thank you for inviting me here. It's the second time I'm visiting, and glad to be back. So this particular talk, or the three lectures that I'm going to give today, tomorrow, and then day after, is based on this work that came out last year, and then based on some of the ongoing works with the three people here that you see, Alexei Cherman, who is at University of Minnesota, Larry Yaffe, who is at University of Washington, and Theo, who is Alexei's student. So I'm going to talk about Higgs confinement phase transitions in 2+1 dimensional superfluids. Okay. Eventually, that's what this talk is going to be about. So what happens here is the following. So I'll tell you a little bit of the history of how we got into doing this. So I work in QCD, nuclear physics, and stuff like that. And I used to be a postdoc at University of Washington. We had a journal club where we used to interact with particle physicists and condensed matter physicists. And going to journal clubs is good. So that's what you will see in this talk, where we can put together ideas. So there are ideas from QCD and nuclear physics. There are some ideas from topological phases and condensed matter physics, which come together to teach us something about Higgs confinement phase transitions. Okay. So let me unpack the title for you a bit. There's a lot of history to the subject that I'm talking about. So first of all, I'm going to talk about gauge theories. Okay. So on the right-hand side, you see a picture of the Higgs mechanism in abelian gauge theories. So what this is showing is the picture of ordinary Meissner effect. So in ordinary superconductors, you have Cooper pairing of electrons when you're below the critical temperature, and that gives mass to the photon, which gives rise to shielding of magnetic fields below the critical temperature. So that's what this is showing, and that's the abelian Higgs model. And on the left-hand side, this picture is taken from the nobelprize.org website. So this is showing confinement in QCD. Now, it may look like I'm comparing apples to oranges, because one of them is a U1 gauge theory, the other is a SU3 gauge theory. But it's just a limitation of the fact that these are the pictures that I could find on the internet. Okay. I couldn't find a picture of an SU3 gauge theory with Meissner effect and a U1 gauge theory showing confinement. So that's what this is. But confinement and Higgsing can happen in both SUN gauge theories, U1 gauge theories, and other kinds of gauge theories. So that clock is not correct, right? So I need time.
No, 10:15.
Thank you. Okay, 10:15. Okay. So let me tell you what I mean by confinement here, although I'm not going to use any of these definitions in my talk. But in fact, I'm going to sort of define what I mean by confinement through in the course of the talk. That's what's going to become clear, what confinement is. But for the sake of clarity, let me say what I mean by confinement. So we know what the Higgs mechanism is. It's like you have a gauge theory, you add to it some fundamental matter fields. Let's say you add some scalars, and the scalars are charged under your gauge group, and so they can gap out the gauge bosons. And so that's your Higgs mechanism. What I mean by confinement is a mechanism of gapping out the gauge boson even in the absence of matter field. So if you took your gauge theory and the matter content and then got rid of the matter content, and you still end up with a gauge theory that has gapped gauge bosons, that's what I would call confinement. Okay. This is a more traditional definition of confinement, and this is going to hold true in the examples that I'm going to show you. So let's say again you have a gauge theory, and you're taking sources that are charged under the gauge group. And so you take a particle and an antiparticle and then pull them apart. And if your theory is confining, what's going to happen is that there's going to be a string tension between them. So there's going to be a string that's going to form. And at some point, as you take the fundamental fields too far away from each other, there's going to be an energy cost that comes from the fact that there's this string tension, and eventually you'll be popping out particle-antiparticle pairs from vacuum when the length of or the distance between the two charged objects is bigger than the string breaking scale. Now, in general, in case of QCD, for example, the string breaking scale and the confinement scale are not very separated. So the idea or the concept of confinement is messy. But in the problems that I'm going to discuss, the string breaking scale is going to be very far away from the confinement scale. So there's going to be a well-defined concept of confinement in the problem that I'm going to discuss. So here's the second part of the title. So I'm going to talk about a phase transition separating Higgs and confining phases of a gauge theory. So people have been thinking about this question for some time. So there was a paper in 1979 by Fradkin and Schenker addressing exactly this question, whether Higgs and confining phases of a gauge theory can be separated by a phase transition or not. And what they showed in their paper is that under certain circumstances, which I will elaborate on later in this talk, the two sides, Higgs and confining sides of a gauge theory, are actually smoothly connected. They are not separated by a phase transition.
Was this in the context of particular models, or was it a quantitative?
It was very general, yeah.
I mean, how can you ever rule out a first order phase transition, for instance?
So what they did in their paper was actually a strong coupling expansion. And what they showed is that if you compute the free energy, you can go from Higgs to confining phases without any non-analyticity in the free energy. And so it was sort of like an explicit calculation.
But that was with the context of some model, right?
Yeah. So I will explain which models those are. So it turns out that the lessons of this theorem are actually invoked a lot of the times outside of the scope. Yes. So invoked outside of the scope of the validity of the theorem, and so it has turned into a folk theorem. And so what I'm going to do in this talk is I'm going to attack some of those wisdom which are ill-motivated. So here is the concrete version of the standard lore. So this is one of the examples that Fradkin and Schenker looked at. And through this example, you can sort of see where their theorem is applicable. So let's say you take a gauge theory and you add to it fundamental matter fields, and then add to it a potential for these fundamental matter fields. And let's say your matter fields are scalars, and you can then dial a parameter in your potential to go to a regime where the scalars have a vacuum expectation value, and they gap out all the gauge bosons via a Higgs mechanism. And then there's another region where the scalars are not condensed and you have confinement. What they showed is that if, as you are dialing parameter to go from one regime to the other, there is no symmetry, no global symmetry whose realization can change from one regime to the other, then there is no phase transition.
And here all the global symmetries are zero-count symmetries?
Yeah, for them that's what they considered. That's right. But the theorem may still hold for higher form symmetries. But yeah, for them it was just.
When you say realizations are the same, can you give an example of realizations not being the same?
Yes, yes, I will do one by one. So,
No, I just wanted to know the language. What do you mean by realizations being the same?
oh, what I mean is that there is no global symmetry which is spontaneously broken on one case, on Higgs side, let's say, and it's not broken on the other side.
Oh, okay.
So then, there would be an obvious phase transition.
You don't mean some non-local realization of the symmetry in one image?
No, no, no. Okay.
So basically, you don't, in whatever they exclude, they didn't find an order parameter that takes a zero value in one.
Right. So,
Will you be going through their model in more detail?
no.
Okay.
So I won't go into the proof of their model, but I'll show you what are the features that they really needed to prove what they proved.
And could you just remind me, my vague memory is that there is a phase transition on the diagram that separates a Coulomb-like phase from a
Yes,
Higgs
yes,
diagram.
yes,
Is that
yes,
right?
yes.
Okay. And it was a two-parameter set of.
Right,
it was
right,
two
right.
One was the gauge coupling, and one was the.
Yeah. Yes, yes. So, so this is one example. Okay.
I'm sorry.
Okay, go ahead.
My memory is that the analytic computations were, if these were the axes, there was analytic computation. Going away from one axis, analytic
Can I
computation.
suggest that she just sketch that phase diagram so that all of us have
Would you be able to?
Oh, that diagram. Okay.
just without proof, just say what you got.
Well, that diagram is not what I'm talking about here at all, actually.
Okay.
So there's no Coulomb phase in here.
Okay, not the Coulomb, but so you said something about what they proved.
Yes.
Can you just translate that into the structure of a phase diagram?
Well, so that's your phase diagram. Okay.
Yeah, no, so but
There is no other. So
what are the
There is-
parameters? There's a coupling parameter between the.
So yeah, for now, what I care about is the coupling parameter. That's all I care about. So there is just one parameter here.
There's a Landau potential for the scalar.
Yes.
There's one
Yep.
parameter in that which we
Yep.
call R, and then there's another parameter coupling the scalar to the gauge field.
Yeah,
Yes.
or the coupling. It's like a U1 gauge field, so the coupling of the gauge field.
Coupling of the gauge field.
Right.
Coefficient of
Yeah.
cosine.
So two parameters.
Yeah. This is compact.
Yes, it is.
Okay, so can we just draw those two axes and so I know what you're talking about? I don't remember this. Okay. So lambda is the coefficient of R phi square of something.
Yes,
Okay.
that's right.
And E square is the coefficient of cosine plus A.
Yeah,
Okay.
most likely. So what I'm not sure about is what happens along this axis. Okay. What I know is that so long as you're dialing this lambda, okay, there is a regime in this whole phase diagram everywhere where your scalar fields have a wave. Okay.
Yeah. So it's lambda phi square and lambda negative.
Right. So there is.
Sure.
So
that
there is no
when
phase
R
diagram.
set to 0, there is a standard transition.
So there is no transition as you go from one to the other,
Set to
provided.
0 there is, right?
Sorry? No, there isn't.
So when I set t to 0, there is no coupling to the gauge field. Is that what the meaning of E is?
Yes, yes.
So then, I mean, it's a uncharged scalar having an Ising transition. I don't understand.
So for that you need a certain global symmetry, right? So what? Oh, okay.
Yeah,
I
mean,
see.
got-
So your gauge theory, okay, your SUN global symmetry in this case will
I
become a
don't know
global
what it
symmetry.
is, I'm just wanting to find out.
Right, right, right.
Yeah, my memory is, I can't remember any details, but my memory is along one axis is the transition you were talking about.
Yeah,
Pure
and then you turn on a charge that couples it to the fluctuating.
Right.
Which turns it from basically Goldstone to Higgs.
Yes.
Yes,
Correct.
yes,
And on
yes.
the other axis, it was just pure gauge.
Right, right, right.
Which were
That's
a
exactly.
confinement transition.
Correct.
And then they argued that the phase transition
Continuously connected.
was that there was something that connected the two, some funny shape. It went like this here, with this cusp here.
Yeah.
And then separating this phase from the outside.
Yeah, just I noticed
Right.
this. That's why I'm clear on what's being talked about. If it's relevant. If it's not, let's forget it.
Yeah, I don't think so. What you're saying is true, that when you
So
set
there
the,
is a transition along the lambda.
there should be a transition.
Yeah.
So, because you know your gauge, your Goldstone bosons are not eaten by the gauge field. That is true.
Yeah.
But it turns out, well, I'm not sure at what E square the phase transition goes away. Or if I were to guess, I would think that whenever you have even a little bit of a coupling between the gauge field and your fundamental matter scalar fields, you know, you wouldn't have a phase transition. That would be my intuition.
So if I
Just a
take
second order point.
No, that can't be true. If I take a charged boson, you're saying.
Yes.
I don't have a superfluid. Of course, I have charged superfluids in two dimensions. That's zero.
No. So it depends on what. So here, as you're
This
dialing.
might be just language. Why don't you go ahead?
Okay.
Yeah.
Okay. So here is the example. Okay, you have an SUN gauge theory with n fundamental scalar fields. Okay. Now, of course, when you have n scalar fields, you can write the scalar field as an n by n matrix. Okay. Now, I'll show you what kind of potential you could write down for the scalar fields. But let's say you are now you have a certain potential, and you can dial the parameter to go from a regime where the scalars have a vev. For example, they have a diagonal vev, okay, to a regime where they don't have a vev. And so as you dial the parameter, there is no phase transition. So that's one thing that they proved. So this is, for example, a potential that you could write down. So here phi is the n by n matrix that I showed you, n equals 3, let's say in this case. So here what you see is that v square is a parameter that can be positive or negative. When v square is greater than 0, it forces phi to have a non-zero vacuum expectation value. And what this term is doing is that it's making sure that phi has a diagonal vacuum expectation value whenever v square is greater than 0. So as you dial parameters, so go from v square greater than 0 to less than 0, you go from a regime where phi has a vacuum expectation value to another regime where it doesn't. Now you might say, why can't I use this object phi to detect a phase transition? Because it has a vev on one side and doesn't have a vev on the other side. And the reason for that is.
Something. If the matter field was supposed to be fundamental or adjoint? Or
It's fundamental.
In number of the fields.
oh,
In number of.
in number.
Yes.
The same n. I mean,
Yeah, it's the same n. Exactly. It's the same n. Yes. So the reason you can't use this as an order parameter is because it is gauge dependent. It's not a gauge invariant quantity. So it doesn't make sense to talk about its vev going from 0 to non-zero and using that as an order parameter. However, there is a little more of a catch here, and this is what Fradkin and Schenker ensured while proving what they proved, is that you better not have a U1 global symmetry under which the phi fields transform. Okay, so these phi's, the entries are complex valued fields, and you wouldn't want them to transform under this symmetry. The reason for that is, although the individual entries of phi is gauge dependent, there is an operator that you can write which is gauge invariant, and that's determinant of this phi field. Okay, this should have been an arrow. It's not an equal sign. So if you do allow your phi field to transform under a U1 global symmetry, then determinant of phi will also transform under the global symmetry.
Phi is a column?
Sorry?
Phi is a matrix or a column?
Phi is a matrix.
It's a matrix.
It's this matrix, for example.
Uh,
So it's an n by n matrix. I had n fundamental scalars.
you had n fundamentals. Thank
So what happens is that as you dial parameter to go from a regime where phi has a VEV to a regime where phi doesn't have a VEV, immediately you also induce the same behavior in a determinant of phi. So in the Higgs regime, determinant of phi has a VEV. In the non-Higgs regime confining side, determinant of phi doesn't have a VEV. So you immediately have a phase transition, which is realized by the breaking of the U1 global symmetry. Okay? So the symmetry is spontaneously broken on one side and it's not broken on the other side. So there's an obvious phase transition, and this is something that Fradkin and Schenker wanted to get rid of, because this is not telling you anything about the gauge theory itself. It's just, it's just coming out of the potential that you had.
This is the simplest gauge invariant operator that is charged under the nucleus.
Yes, exactly. So they got rid of that, okay, and that's kind of.
This is roughly like monopoles in some sense. The contract in all of them. You have exactly a number of them, so you can use SU and epsilons to make a singlet. It's like the monopole of
Yeah.
What do you mean they got rid of it, please?
Right. So there are two things you can do. The thing that I am comfortable with is to take the Lagrangian and add operators that break the global symmetry explicitly. What they did was they were doing some path integral and to prove their theorem, and they restricted the path integral over those kinds of field configurations which are just SUN valued, and didn't.
You can just gauge UN, then you don't have this global symmetry.
Let's not go there right now, because the story is very different. I will gauge the U1 eventually on the third day maybe, and then you'll see what happens. Okay. Okay. So here's what was done before and what we want to do. So we want to keep the U1 global symmetry, and we want to keep the symmetry spontaneously broken on both sides. Okay. And then we want to ask the same question: is there a phase transition as you go from Higgs to confinement phases? Okay.
So should I now think of a boson that is actually charged at a fluctuating U1 gauge field which is compact? That's the model.
Yes. Yes. Yep.
2 + 1.
Yep. But that's going to eventually come. Right now, I haven't gone to 2 + 1D yet. Yeah. It's going to be a yeah. Yeah. Yes. Yes. Yes.
Ground state or state space to open edge.
Sure. Sure.
Just say it again,
Charged boson in 2 spatial dimensions, charged under a U1, which is a dynamical U1 compact cosine Curlane plus E square. Is that what we're talking about?
In this model?
Yeah. I mean, this could be an example of what he's saying is what I'm asking. I just need one example to keep.
The example is going to come, but it's going to be similar to what you say. It's not going to be exactly the same thing,
But
because
what
it's.
you're saying would apply in that.
Yes,
case,
yes.
then I
Oh.
can try translating.
Well, you also need to have Higgs and confinement and so on and so forth, right? For this whole thing to.
Yes, of course.
So I'll have to add more field content to make it richer than what you just said.
Like scalar has a phase transition where you break them. Right? So
Yes,
that part
yes,
is there.
yes, yes.
Cosine Curlane plus E square has a transition.
Yeah.
So
For the first part, for the Fradkin Schenker part.
Yes.
Right? Yeah, that I
Right.
think is a perfect.
that is a good.
That sounds
Yeah.
perfect.
Then
Yeah.
there's going to be more stuff.
Right, right.
I want some foothold.
I think that's what my memory is. That's what Fradkin.
That's what I thought so. Yeah.
Maybe U1. Compact U1 is basically as good. I can't remember whether they looked at SU2 or
But how would there be transition in the lambda equals 0 axis?
because it's compact U1.
Or compact?
Right.
Yeah.
Yeah.
Just one thing. What does it exactly mean, this theorem, that you cannot find a order parameter? What is the claim? What is the assumption? What is the claim? Can you state that?
So what are you asking me?
I want to know what are the assumptions and what is the claim. You are saying that there is no phase transition. It is based on what? That you couldn't find a order parameter?
No. So for them,
Mhm.
for them
They
is
did a
that they
lattice
act. Yeah, they did a lattice model.
You can
And
do analyticity in the strong coupling expansion.
Exactly.
There's no transition encountered in some arc. And
Yeah.
this is-
so it's continuously connected. There could be in some parts of the parameter space there could still be a phase transition, but
Some part is controlled and the
Yeah. So really the set of words that should be used is that are they continuously connected or not?
Yes.
Right. And what they proved, Fradkin and Schenker proved, is that there is a path in parameter space along which you can connect the two phases.
So this is what you meant by saying that's what they proved, but it's become a folk theorem. People assume there's nothing anywhere.
Well, no. What people do is that they say that there is. So Higgs and confining phases are not are not separated by a phase transition or are smoothly connected under all circumstances where there is no realization. There is no global symmetry whose realization is different on the two sides. That's what people say.
Yeah.
And what we're saying is that actually that's not necessarily correct.
Okay.
It could be that there is no global symmetry whose realizations are different on the two sides, but there could still be a phase transition, or there could still be a phase transition, or the two sides would not be smoothly connected at all. Okay.
There'll be some transition.
There would always be transition, is what we are going to claim eventually, under certain circumstances, even when there is no global symmetry whose realizations are different on the two sides. So there is a non-trivial. Sorry?
How about when there is no global symmetry?
So when there is no global symmetry at all, for that you have the theorem of Fradkin and Schenker. Okay.
So it's not a model dependent statement, it's just a theorem. When there is no global symmetry, there is no phase transition.
So there's is not, you can't really take it as a theorem, but people treat it as a theorem. So it was not proved in as, it was not as general as it seems like, but people treat it as a theorem. If there is no global symmetry, there is no phase transition.
But let me phrase it differently. So when there is no global symmetry, do you find models where there is a phase transition?
No. I need the global symmetry and I need it spontaneously broken on both sides. Okay. So the realization of the symmetry is same on the both sides.
But still their result doesn't.
Yeah, so what I'm going to find is not going to contradict their result,
Okay.
because they didn't have the global symmetry in the first place. Right? They got rid of for example, in this case, they got rid of the U1 global symmetry. So what happens when you allow for the global symmetry and allow it to spontaneously break on both sides, it allows you to have certain probes which were not available to Fradkin and Schenker. And so what I'm saying is that whether the two sides are smoothly connected or not depends on the kinds of probes that are allowed in your theory.
Can the global symmetry be discrete?
Yeah, so this is a question to think about. Our guess is that it can still work if it's a discrete symmetry, but we haven't thought about it. Yeah.
The Fradkin Schenker, how did they get rid of the U1 by adding this additional operator or gauging it?
They didn't. What they did was to when they did their path integral, they restricted their path integral only over certain field configurations. That gets rid of the. Yeah, so that's another way of. Which one are you talking about?
If you take a U1 model with one fundamental field, then there's no global symmetry.
There's no global symmetry.
Yeah.
That's the classic.
Right. So that's not I'm talking about. Yeah, that's not what I'm talking about.
So I could have two charged scalars and let's say there's some symmetry under rotation among them, which is not.
Right. So forget the U1 model. There is an SUN model that's described in Fradkin and Schenker, and you can see what they do there is that they restrict the path integral in such a way that you wouldn't.
Global U1 they don't take it.
Yeah, exactly. Okay.
So both these phases are superfluids?
Yes, that's what I am.
So could it be imagined as like in Kelar's example? So you have a Kelar.
Yeah.
Could it be like a super insulator to superconductor kind of transition?
I haven't gotten that far in the translation. I was just trying to understand the connection to fractal.
So if you
Right,
have
right.
vortex-like excitations on one side and they condense, and let's say you have Foucault pairs on the other side.
Yeah. So it's
Both are superfluid.
both are superfluids, and it's really the vortices that are going to tell the difference between the two sides. Okay. So when you do Fradkin and Schenker, you can't have any vortex-like excitations because you don't have any global symmetry. In this case, you're going to have such excitations, and they will be able to tell you the difference.
But
So
you
that's
are
sort
in
of
2 plus 1 dimensions. So even
not
if you-
yet, but yes, go
but
ahead.
If you are in 2 plus 1 dimension, even if you gauge U1, you have a topological U1, which is a global symmetry.
So
So then that is a global symmetry. You can have order parameter with respect to that global symmetry.
right. So I don't want to do that. I want to do what I want to do is I want to make sure that there is no global symmetry whose realizations are different on the two sides, and then I'm going to show that there's a phase transition. That's what I don't want
Your
something that can.
vortices will not be charged under this topological U1.
No. Okay, so you can take the same example that I was showing you, which is that SUN gauge theory, and you're dialing parameters to go from a region where phi has a VEV to a region where phi doesn't have a VEV. Sorry, the other way. Here the phi field has a VEV, here it doesn't. But I want to have the following thing to work, that determinant of phi has a non-zero VEV on both sides. So I have to do something to the potential that this happens, okay? So that's what I'm going to do now. So how do I do that? So I'm going to add another scalar field, phi 0, charged under the new U1 global symmetry, which is the charged scalar field you were talking about. So I'm going to add a new scalar field, and I'm going to get it to condense using a Mexican hat potential. Okay? So I'll keep it condensed. And then I do the following. To the potential that I had, I'm going to add a coupling between this scalar field, complex scalar field, and the determinant of the phi field. And the charge of this phi naught is such that it transforms the opposite way determinant of phi transforms under the U1 symmetry. So what this is going to do is the following. This is going to tilt the potential for the determinant whenever phi naught has a VEV. So irrespective of whether phi has a VEV or not, determinant of phi is going to have a VEV whenever phi naught has a VEV. Okay?
So phi is a vector of bosons that transfer under the fundamental of SUN. Is that what it is?
So are you talking about phi naught or phi?
Sorry, phi naught is the new one.
New one.
The other one?
So the other one, phi, originally in case of Fradkin and Schenker, it was just n set of SUN.
Yeah.
Now I'm going to allow it to transform under a U1 global symmetry.
Okay.
So this is a change.
Phase.
Exactly. Phase rotation.
And
And
it's coupled like this.
exactly. Yeah.
Now,
Yeah.
if I try to translate that into what it means for the interactions between these capital phi particles and the phi naught particles, it sounds very weird.
It is. Yeah.
Because it's a determinant.
Right. Yep.
All right.
So presumably you could get it this phi naught as the Hubbard Straton-Lubitsch field with the determinant phi mod square potential.
Yeah, you could do that, I think. You could. We didn't do it, but you could probably do that. Yeah.
Because then you wouldn't need to introduce some additional field in the
Well, yeah, I guess so. But it's it doesn't harm doing this. It makes it clear for us. Okay. So let me summarize what I want to ask. So the question is, can there be phase transition between Higgs and confining regimes when there is no symmetry realization that can distinguish the two sides? And this I didn't talk about at all, which is that number of gapless modes on the two sides are also going to be the same. These two statements are sort of interchangeable in some sense, but depending on the context, one or the other is easier to use. Now again, in case of Fradkin and Schenker's example, the cases that Fradkin and Schenker considered, you saw that actually the Higgs and confining phases in those examples are smoothly connected. But I'm going to claim that there are some other examples where they are not smoothly connected. Okay? And this is what these lectures are about. So who cares? So if you're interested in gauge theories, particle physicists, condensed matter physicists, whoever is interested in Higgs and confinement should be interested in this. Now, this is about how I got into this, thinking about this question. And this is, this comes from the fact that I was thinking about the QCD phase diagram, okay? So what is the QCD phase diagram? It tells you what happens if you take this chair, for example, and if you heat it to extreme temperatures or crush it to extreme densities, how does matter reorganize itself? So that's what this diagram is capturing. Now, the temperatures or densities are so extreme that how matter is reorganizing itself gets dictated by the physics of strong interaction. So that's the only physics that this diagram is capturing. Now, I'm not going to talk about the high temperature part of the phase diagram at all. I am mostly considered about the extreme density part of the phase diagram. So the x-axis is, it's the baryon chemical potential, which is a proxy for the baryon density. So, let's say you take an ordinary material and you start crushing it to extreme densities. What happens is that at some point, the atomic nuclei start releasing neutrons and protons, and you get a Fermi liquid of neutrons and protons. And on top of that, what happens is that there's Cooper pairing of nucleons at the Fermi surface, which gives rise to superfluidity. So what happens is that you get a nuclear superfluid. So this is nuclear matter, and it breaks baryon number symmetry, which is a U1 symmetry, down to Z2, okay? Which is what gives rise to superfluidity.
I'm really sorry to interrupt again, but I didn't understand the dead phi anytime. So phi is not the gauge field, right? It's not the SOA gauge.
It's not a gauge
N
field.
copies of a fundamental field. N different fundamental fields. Each fundamental field is a column.
Is a column. So there are
And there are N different. So there's an N. The flavor symmetry is SUN also.
Yes.
Same
And there are
Same
Same.
Right, right.
That's why it
right.
makes some kind of
So you just take the field configuration of these n square scalars and take its determinant.
Mhm. Yeah.
Note that it's the lightest operator, simplest operator that is gauge invariant and charged under the global U1.
Yeah.
Because you see, to make a gauge invariant, you would normally take a phi and a phi bar.
Correct.
And that's automatically global U1 neutral.
Yeah, you
Right.
want it to be not neutral.
Yeah.
But det phi is invariant under the gauge group,
Yes.
but it's non-invariant under the global U1 because it's charge N under the group.
Yeah.
N charge,
Yeah.
So you have a minus n charge
In
scalar.
phi.
and you add it.
Right. Yep.
So this is an all-to-all coupling between n square flavors. and-
Yeah.
Yes. Between N flavors, N colors.
Yeah.
So n square different objects,
Okay.
all-to-all coupling all over space.
But it's
Yes.
the simplest way you can do it in a gauge invariant way,
Right.
such that it's U1 charge.
And yeah. And you will see why we are writing this crazy thing, okay?
So it's like the electric charge of the barrier.
What do you mean?
So it's a different U1.
Yeah, it is a different
Baryon
one.
is- baryon is like the determinant.
Right. Yeah. You will see that here actually, exactly the same. Okay. So here you will see an example where this happens. Okay. So this is QCD where this thing happens. That's why I'm writing this weird model. So at low density, you have nucleon baryon pairing, so you get superfluidity, as I said. And then as you go to even higher densities, what happens is that quarks get released from the nucleons. So you get something what is known as quark matter. And again, there is Cooper pairing between two quarks at the Fermi surface. And the corresponding phase of matter is known as color flavor locked phase of matter. And again, the way Cooper pairing happens at the Fermi surface, that breaks baryon number spontaneously. Okay, so again, you get superfluidity on the quark matter side. Now, what one can do is the following: the quark superfluid can actually be mapped to the problem that I showed you earlier, where you have this, let's say, SU3 gauge theory with 3 fundamental scalar fields. Okay, so and the quark matter side maps to the case where that 3 by 3 matrix has a vacuum expectation value. And also determinant of this 3 by 3 matrix has a vacuum expectation value. And the nuclear matter side maps to the regime where the 3 by 3 matrix, scalar field matrix, does not have a vacuum expectation value, but the determinant of that matrix has a vacuum expectation value. And I'll explain where that comes from. So basically, the quark matter side maps to the Higgs side, and the nuclear matter side maps to the confining side. Surprise, surprise. Of course, that's what would happen if there would be a mapping. So the question one might ask is that as you're dialing parameters to go from nuclear superfluid to quark superfluid, is there a phase transition separating the two? And this question was actually thought about by Thomas Schaefer and Frank Wilczek in 1999. And what they concluded is that there is no phase transition. Most likely there is no phase transition. So this was a conjecture. And the reason they made that conjecture were twofolds. The first was that they were motivated by the theorem of Fradkin and Schenker because of this mapping that I told you about. And the second was that if you compare the global symmetries and how they're broken on the two sides, the nuclear matter and quark matter side, you will see that the symmetry breaking pattern is identical. And so they said that, okay, there is no phase transition separating the two. Now, the interesting thing.
For these 5, what are the indices? These 5 entries?
So these are, again, color and flavor indices. And you'll see.
So you're doing 3 flavor.
Yeah, I should have said it. So I'm looking at QCD with 3 flavor quarks, and they are degenerate with each other, okay?
And these are now fermions.
The phi is going to be a scalar, and you'll see where the scalar is. Basically, it's going to be Cooper pairs of quarks, okay? So that's what this is. And now the interesting thing in this case, go ahead.
The quark matter side is perturbative, right? So it's under complete control.
Yeah.
The nuclear superfluid side is very strongly coupled.
Yes.
So that sort of works, right?
Yes, that's right.
Yeah.
One thing that's different. So by the way, that's one of the reasons why you really can't do a calculation like Fradkin and Schenker did in their thing. When you have real QCD with quarks, it's messy. The confining side is really messy.
What would happen if you consider 2 flavors?
There is, the gauge group is not completely Higgsed in that case. Okay, so there is a phase transition then, because on one side you have complete gapping, on the other side, you have some parts of the gauge group that's broken and part of it that's not broken, and that's a different thing altogether.
I'm sorry.
Okay.
Just to, maybe you will get to this one, but how you construct this phi out of 2 quarks is not clear to me.
It'll
Because,
yes.
Like QI alpha, QJ beta.
Yes.
and how you- yeah.
Wait.
Right.
Let me go ahead, because otherwise I'll be late. So when they made this conjecture, what is important to notice, which I wouldn't say they didn't notice, they did notice, but if you were considering only local order parameters and global symmetries, you wouldn't care. So as I said, in case of Fradkin and Schenker, there is no global symmetry in their problem. But in this case, there is a global symmetry, and that's spontaneously broken on both sides. But again, if you were only worried about local order parameters and global symmetries, you would think it wouldn't matter that that this symmetry is broken on both sides. You would think that their result would still apply. Fradkin and Schenker's result would still apply.
Only local order parameters?
You will see that. Okay. Why care about local order parameters is a historical. It's a historical thing. Okay, people have, it's the Landau paradigm, and that's what people have been used to. This paper was 1999. Okay, so there is a history there. So basically, that's what's going on.
So the breaking of the global U1 symmetry is because of the chemical potential, right?
No.
So please, I haven't understood why the U1 symmetry is broken.
Oh, that's because of the pairing at the Fermi surface.
He has given a potential to this additional scalar.
Not here. Okay. this not in QCD. It's happening because of the fact that you have the instability, which is how Cooper pairs form. Okay, so there is an instability on the quark matter side. This you can actually perturbatively compute. In QCD, you can see that there is a Cooper's instability, and so that gives rise to.
Sorry, the chemical, the mu is coupling to precisely this U1, right?
No, mu is, so putting mu breaks charge conjugation, okay, explicitly. But so which operator is this? Okay, so when I'm saying that this global symmetry is spontaneously broken, it's this operator, which has a non-zero wave. So if these are baryons, right? So these two transform under the baryon number symmetry. The chemical potential is mu, right? So this operator does not breaks charge conjugation.
So what that dagger, that's the complex conjugation?
Yeah. Right. The psi bar gamma 0 psi is what here says.
Baryon number will be 0 there.
No, there is baryon number. That's why you have finite density, right? So you have some finite number of baryons in your system.
No, but side kind of thing. This is the baryon number of side
Yeah.
That's what they totally put it in the.
So you get Fermi C because you have more quarks than anti-quarks, right?
Yeah. Yep.
That's a consequence of the
Chemical potential.
Chemical potential.
Yep.
But that you don't consider breaking the U1 symmetry.
No, that doesn't. So this operator will produce what you are saying. This does not break the baryon number symmetry, right? Okay. So now I'm going to tell you what the mapping is. Okay. So you have Cooper pairing of quarks at very high density. That's where it's easy to see what I'm talking about. Okay. So this is how the pairing works. So you have Q is the quark field.
Yes.
So I and J are color and A and B are flavor indices, let's say.
Okay.
So the channel in which pairing happens is this channel where you have, it's completely antisymmetric under color exchange, completely antisymmetric under flavor exchange, but symmetric under both color and flavor exchange, okay? So you have 4 indices, as you were saying. So this phi is a scalar field with 4 indices. But now what you can do is the following. You can write it as a color antifundamental by contracting the 4 index thing with appropriate Levi-Civita. And so now this phi is the 3 by 3 matrix, okay? Yeah.
So this 2 index is dual to 1 index.
Yes. So this phi now stands for pairing of 2 quarks. So it's a boson in that sense.
I'm sorry, both of us are spacing out. Could you?
So I'm telling what the mapping is here. So it's very easy to see in the high density color flavor locked phase. So here you have Cooper pairing of 2 quarks, okay? So Q is the quark field. You have I and J are color, A and B are flavor indices. And the pairing happens in this particular channel where color indices are completely antisymmetric, flavor indices are completely antisymmetric. But if you were looking at the order parameter, you would see that it's symmetric under both color and flavor exchange. Okay? And so it's a 4 index object, 2 for color, 2 for flavor. Now what you can do is that take this 4 index object, which is a bosonic object, and contract its indices with proper Levi-Civitas to write it as a color antifundamental. Okay? And so now you get this 3 by 3 matrix. Every entry of it is a 2 quark object. So it's a Cooper pair of 2 quarks written as a 3 by 3 scalar field.
It's basically a bifundamental stuff.
Yep. That's what it is. Yes. Okay. So now this object is a gauge dependent object, right? And it getting a VEV, vacuum expectation value, doesn't tell you anything about phases and phase transitions. Okay. Now, so whenever phi has a non-zero vacuum expectation value, you would expect determinant of phi to also have a non-zero vacuum expectation value. Now, of course, phi itself is a pairing of 2 quarks. What is determinant of phi? Every single entry of this phi matrix is a 2 quark object. So if you took a determinant, that's a 6 quark object. So that's like pairing of 2 baryons. Okay. So when you have pairing of two quarks, it immediately translates into pairing of two baryons. Okay. So this operator, so this phi operator is gauge dependent, so it may not make sense to talk about this operator breaking global symmetries spontaneously, but the determinant of phi is again gauge invariant, and that breaks baryon numbers spontaneously. So that happens in the quark matter phase. Now, on the nuclear matter phase, nuclear matter side, phi does not have a vacuum expectation value, but there is enough proof already in, from nuclear physics and some lattice data.
Sorry, and roughly you said it's this phi guy that becomes delta in your quark matter phase.
What is delta?
Delta
In
L.
diagonals.
Yes, yes, yes. So, yeah, so this is what happens. In the nuclear matter side, you have pairing of baryons, which translates into determinant of phi being non-zero, okay? But remember that on the nuclear matter side, you can't do a controlled calculation, but there is good enough reason to think that this is what happens, that there is pairing of baryons, okay? And also,
roughly the phase transition to nuclear matter happens when the chemical potential is the mass of the lightest
yeah,
nuclear.
exactly.
So it just condenses.
Right, exactly. And so you see the difference between quark matter and nuclear matter is that this gauge dependent thing is non-zero on one side, zero on the other side, but the gauge invariant object, the only gauge invariant object you could write down has a wave on both sides. Okay? So there is no local order parameter which can tell the difference between the two.
Sorry, and what I said about the chemical potential with nuclear matter being the mass of the lightest nucleon, is that a rough statement or an exact statement?
It's a rough statement. To be honest, there is more details in there actually. So if the particular limit that I'm talking about, it's three degenerate flavor limit, and in that limit, the lightest particle per baryon number is actually a boson. It's called the H dibaryon. And so once you go, your chemical potential goes beyond the mass of the H dibaryon. It's a boson, by the way. In that case, it's not even a BCS. So the moment your chemical potential goes beyond the mass of the H dibaryon, you get a BC. Okay, it's not even a BCS. So I'm sort of putting a lot of stuff under the carpet because there's details that if I went into that will take away from the talk that I have. Okay.
When you write phi Lm equal to 0,
Yes.
do you mean that it takes infinite energy to excite them in that sense, like a Polyakov loop being 0?
Yeah. It's yes.
Not
That's
quite
right.
phi Lm equal to 0.
Well, phi. So.
What do you mean? Yeah. Oh, I see. So okay, the same as the Polyakov loop, I guess.
Phi. So.
Yeah,
You
no,
could.
I'm trying to understand
You could say that's going to happen, but I would say that this is a consequence of the fact that phi is going to be 0 in that case. So if phi wasn't 0, right, you would have Higgsing even in nuclear matter phase.
Yeah,
okay?
I'm saying that like if it was just a mathematical statement,
Right.
then it would be something weird, right? Phi Lm
So okay, I
equals 0.
mean the vacuum expectation value of this,
Yes.
right?
So when the vacuum expectation value comes, presumably it's a statement of the corresponding Polyakov loop being 0. Is that or no?
I
What-
don't think
I mean,
so.
Gautam thinks a gauge dependent operator.
Yeah, so that's
is that an intuitive statement or is it a precise statement?
no. It is so fix a gauge, fix any gauge, okay,
Yeah.
and this is going to be 0. Okay, and this is
But it's a theory only of the singlets.
so you don't have to think about this SU3 gauge theory. Just think about U1 gauge theory, a William Higgs model. Okay, so you're dialing a parameter to go from a region where your scalar field has a wave, where it gives Higgsing. It causes the abelian theory to get Higgsed, and there is another region, right, where your scalar field, which is charged under the Higgs charge on the gauge field, is not able to Higgs the gauge field, and that's because it doesn't have a wave, right? If it had a wave, right, you would immediately give mass to the photon, right? So that's all I'm saying. That this is a region where
But in the confined phase, I should not talk about waves of colored objects.
why?
because my picture would be in fact indeed this way, that you can't isolate such
Right.
degrees of freedom. You
Right.
can't simply create them.
Right.
And that I would be happier with that kind of a statement rather than saying
So-
that they're fair is equal to zero.
So I will tell you what I mean. Maybe that's the same thing as to what you're saying. So I had a potential like this for the scalar fields earlier, right? So I'm driving this v square to go from positive to negative values. So whenever v square is positive, I fix a particular gauge, and in that gauge I get this kind of vacuum expectation value.
Classically.
Classically, yeah.
But isn't that, I think I have the same discomfort as well. I mean, these are approximate classical statements.
Yes.
To make them precise
Yes.
is hard, right? Okay, or maybe it's some statement about a very complicated gauge invariant operator in the end. Because you're saying fix a gauge and then
Yeah.
everything is physical, but then if you try to make that gauge invariant some crazy.
No. Eventually, you want to compute something that's gauge invariant.
Right.
Okay. And what I'm saying is that, as this is perfectly fine to fix a gauge,
Yes.
and then write your vacuum expectation value for your phi field,
Yes.
whichever field it is, in that particular gauge, and then compute whatever you want to compute. And let's say I don't think that phi having a zero vacuum expectation value itself is a gauge dependent statement. But if you're saying that that's a gauge dependent statement, I'm fine. Yeah, so phi being non-zero, like what non-zero value it is, that is a gauge dependent statement, I think. Because phi dagger phi is going to have a vacuum expectation value the way I have written, okay?
No, but if you say this thing is I'm yeah. Okay, all right. We'll
Okay.
go. We'll
Any gauge statement is true? I thought you need to fix to certain gauges to get to this.
Sorry?
You said you fix to any gauge and you will get this.
No. So I'm saying that this, the form of this, the form of this is gauge dependent on this side, but I don't think this is gauge dependent. If you did a gauge transformation, exactly, that's what I'm saying. Exactly, right?
But why couldn't you say this in Fradkin, Shankar?
Yeah, that's what I was asking.
Why couldn't can you repeat?
If you're saying that there is a way of giving meaning to whether phi is
It's
zero.
I am saying that it doesn't have a meaning.
It does not
okay?
have a meaning.
It
That
does.
I think we're all-
It does not. That was the whole. So that's the whole point of.
We were just
this
uncomfortable
part.
that you wrote down phi lm is equal to 0.
Yeah, that's my only problem.
I'm saying that you can write this down, but you cannot use it to tell whether there's a phase transition or not.
Which
okay?
means that it is not physical.
It's not physical.
No,
Yes,
okay, well.
that's what I have here. Okay,
Okay,
that's
good.
what I mean.
Good.
Yeah.
That's the whole point of this. Okay.
I'm sorry.
All right. So what do I want to do? I actually want to be able to detect Higgs mechanism. Okay. I know that I have no local order parameter, which is being able to tell the difference between the two sides. So how do I look for such operators? So one thing I have to keep in mind is what is Higgsing? So I have a macroscopic gauge-dependent wave function. Okay, so that's what Higgsing is. Macroscopic gauge-dependent quantum wave function, and I want to be able to detect that using a gauge-invariant probe. Okay, it looks like it's not possible, right? It looks like there's something contradictory about this. Turns out that there's no local probe that can do it. That's what I was showing you earlier. Okay. But
So the Meissner effect you call a local or a non-local?
do you want to use Meissner effect, that effect itself?
I'm trying to understand that. By local probe, you mean correlation function of some locally defined operator?
Yeah, that's what I mean. Yeah.
So in that sense, is the Meissner effect a local probe or not?
I mean, what is the operator that you want to write down?
Well, it's the diamagnetic response.
superfluidity.
Diamagnetism is a correlation, and in linear response theory has a correlation constant.
Yes.
So is that
I don't know. So
what is the restriction you are imposing on yourself?
right. So
But Kedar, that's non-local.
That's what I'm trying to understand. Language, not disputing facts. Just saying.
right.
I suspect you're leaving the high energy theorists behind. Oh, what do you mean?
Meister
Can
effect
you word it in
is
terms of
simply you
correlation?
apply a magnetic field and it gets expelled, right?
Yes.
That's a perfect diamagnetic response.
Yes.
Mhm.
Now so that's, you calculate the susceptibility of this hunk of matter.
So some 2-point function.
It's some integral of some 2-point function defined in some way.
Integral of 2-point function is lovely local object.
So then I'm just wondering.
So are you? So the thing that you're talking about is
Yeah,
it's the ordinary Meissner effect, right?
Yeah.
So in case of, I will come to that as well.
Yeah.
But in case of ordinary superconductors,
Yes.
there is a phase transition. There's an obvious phase transition if you counted gapless modes. Okay. So
counting gapless modes involves being some little fellow who goes inside and looks a measure. But I'm saying this is a very macroscopic.
right.
dynamic measure.
So what I'm going to say is the following. What I want to do is I want to get rid of all obvious ways to tell there is a phase
No, I
transition.
understand. But is the Meissner effect one of the obvious ways for you? That you want to get rid of?
Yeah, no. So
That's all.
Meissner effect. Okay. I'm not going to use the Meissner effect as something that detects a phase transition because I'm going to have. So, for example, the example that I showed you, SU and gauge theory, there is a Meissner effect there
Good.
on the Higgs side. Okay.
And not on the other side.
Not on the other side.
But that's not for you a good enough distinction?
Yeah, that's not. So for
It's a yes-no distinction. Why isn't it good enough?
so if you got rid of the global symmetry, the U1 global symmetry that spontaneously broke, the Fradkin and Schenker theorem would prove to you that there is no phase transition,
But there
despite
would
the
still be
fact that there is a.
Meissner distinction.
So Meissner effect for what?
Yeah, so that's the question.
Which you.
Because the field is gauged now, right?
Yeah.
Right, exactly.
Meaning we're not doing a superfluid.
Yeah.
It's gauged, right?
Everything is gauged, yeah.
Let's take the Fradkin checker.
Yeah.
There is only one. There's no global symmetry.
Yeah.
There's a U1 gauge field which you're doing a path integral.
Yes.
Okay, so now tell me what your Meissner. What?
So,
Something to do with some Higgs and kind of operator is.
no, so that's what I'm trying to understand. So I know that that's how you will think. Vikram will. Vikram, charge superfluidity 2 plus 1.
I got it in terms of a
Not superfluid, gauged.
Gauged.
By gauge, what do you mean?
Meaning the U1 is not a global symmetry. You're doing
I
a path
understand. That's why
integral.
I'm saying charge superfluid.
Okay, fine.
In the sense that I have a
It's a superconductor then,
there's
right?
a fluctuating electromagnetic field
Maxwell
and some
charge.
cavity
Yes,
and
yes,
then
yes, yes.
so that's why I said charge.
Yes. So this is certainly something Fradkin Schenker must have thought about. Their statement that there's no distinction
There's no, yeah.
must include your statement.
So then there's a Meissner effect throughout there? Or?
Yeah,
No, that's
No.
the point,
Is it?
right? On one side there's Meissner effect, on the other side there's confinement. And the claim is that there is no phase transition.
Yeah, so but what? So any correlation function you write down cannot be qualitatively different on the two sides.
Right, it's going to change smoothly,
That's what
okay?
Yeah, I mean,
It's
it must be.
a question.
Yeah, I don't understand why.
Yeah.
Okay.
Okay.
But I think that must
So
be.
this is a very unless I'm confused on the Ganesh effect. Vikram, is there a Meissner effect when I have
Yeah,
actual?
but I thought it was non-local, but Kedar
Any
sorry.
local non-local chhodo, is there a Meissner effect?
Yes.
Just keep words in terms of correlator. Say what you mean.
Diamagnetism. No. So linear response theory will relate
FMU,
current correlator.
Current
correlator.
Higgs and the Coulomb phase.
It's a local thing.
Current and what are you supposed to see?
Higgs and the
In the current correlator.
Photon will be an exponentially
That's just a mass gap.
Yeah, that's the
You see the
mass
mass
gap.
gap is confined.
That's what he means.
Yeah, so then what are we looking at?
There's going to be a mass gap on both sides,
See,
yeah.
are you just looking at the mass gap? Does the mass gap to be confined to
I
any?
think it's the
Exactly.
superfluid.
Yeah,
So it's the difference between the Higgs
Yeah,
and the
Higgs.
Coulomb phase, I think.
No, that I follow, but I'm saying if there's a Meissner effect then on the Higgs side,
Because the confined phase also has a mass gap, right?
Yeah.
so there's a Meissner effect throughout. Is that
It's not Meissner, okay, I don't know, you want to
If you mean mass gap of the photon,
perfect? Magnetic
Must
field
have
is
the
expelled throughout in that.
Yeah, it will always.
Yeah, okay.
Always,
Yes.
right?
Yeah,
Yeah, that's
So
right.
That's why it's not a distinction.
yeah.
It's not that it's there on one side and not.
I think so. Yes.
Okay.
As long as it's statement of mass gap, that's what it's talking.
Yeah. So remember my third slide. That was my third slide. Okay.
Yeah. That's on the Higgs.
So
The confinement side, there's also a micro effect.
yeah, I only care about mass gap, and there is mass gap on both sides. Okay. Okay.
Is it the same field that is being expelled, or it's a different field on the two sides?
It has to be the same because it's the gauge field
Yeah.
that has mass gap on both sides.
Take the U1 theory. There's no global symmetry, there's only F mu nu.
Yeah.
Two-point function of F mu nu is basically fixed in index structure, but could have a mass gap. You'll have a mass gap also.
Yes. Normally the mass gap on the confinement side, I think of that as glue ball mass and stuff like that. So in case of the U1, there's some.
There's going to be
decaying Wilson loop. That's the point.
right.
Decay Wilson, so it's because of this complex U1.
I'm sorry for being so rude, but in 15 minutes we have another talk, so maybe we can think about starting to wrap up, though you probably reached halfway for you.
Yeah. Okay. So
Okay, I'm sorry, I read this something.
no, that's okay.
No, we 3 lectures, so we all have. Yeah. That's the point of it.
But can you end by saying where you are going to go?
Yeah.
Some of us will
Yeah.
I mean, not right now, but maybe.
Depending on your answer.
Yeah, I think so. So I can actually give the answer right now, and
That's a bad strategy.
yeah.
Let these guys come back.
No, that's okay. That's fine.
It's interesting that we wait for why that's the answer.
So the answer, I'll tell you what order parameter that can tell the difference between Higgs and confinement side when you do have these global symmetry. Okay, the thing that I was talking about. So basically, you take. So this is the answer. So Wilson loops around global vortex-like excitations will be able to tell the difference. Okay. So what is a vortex? Everybody is familiar. A point around which the phase of the U1 global symmetry is going to wind in space. Okay. Could this work for Fradkin and Schenker? No, because there is no global symmetry. For us, there is a U1 global symmetry, and so you have to compute the Wilson loop. Okay.
Wilson loop of the gauge field.
Yeah.
Okay.
So now you have the answer. You can go. But let me tell you how this works for the SUN example.
And it's going to be either 0 or non-zero in the 2 different phases.
Yep. 1 and not 1 on the 2 different phases.
So will this affect how the vortices interact with each other?
I don't know. I would think that they would, because in one case you have something like a magnetic field inside the core of the vortex. On the other side, it's not. There's going to be no magnetic field at all, anywhere. Okay. So you will see what it. So now you will see what it means. What is the difference between confinement and Meissner mechanism in some sense? So
So is this an indication of some other symmetry?
sorry.
Is this an indication of higher form symmetry?
For this example, we looked for higher form symmetries. There is nothing we found. Okay.
But usually the stability of Wilson loops is similar to that, right?
Usually, yeah, but here, yeah, we didn't, yeah. Yeah, so I don't know if I'll be able to get to the 2+1D model, but that's
So
where things
again,
are.
remedial question, if I can ask one.
Yes.
In the Fradkin-Schenker U1 case, where there's no global thing left over, vortices interact throughout.
There is no vortex for them. There is no global, are you, yeah, so what kind of vortex are you talking?
What they're doing is putting on the boundary, in the field theory, they're putting a vortex of the global symmetry.
Yeah.
They turn on gauge field coupling to the global symmetry, make a vortex for that. Okay, and then put a dynamical Wilson line around that. And that combination, if I understand right, is going to have be one and not one.
Yes,
Is that right?
yes.
So this is different from looking at vortices in the superfluid.
Yeah.
Hang on.
Is that right?
Vortex of the global symmetry is the superfluid vortex.
Well, it'll be linked to that.
It is, so
in the simple example which you are not doing, vortices in the superfluid, when the superfluid is made of charged particles interacting with the fluctuating vortex, those vortices do not have a log interaction. They have a short length interaction. That's why there is no.
yeah, these are going to be logarithmically.
These will be in one. So will they be log interacting in one phase?
In both phases, they are going to be log. Both phases, they are going to be log, but the only difference
Yes.
is
Yes.
going to be the Wilson loops. Okay, that's okay. So okay.
You have another 5 minutes.
Okay. So, for example, for the SU3 gauge theory, it's the determinant of the phi, which is the 2 baryon operator. I want it to wind around a point in space, and then compute Wilson loops around vortices, around this kind of configurations. Okay. So, on the Higgs side, you can actually do a computation. On the non-Higgs side, I can't do this computation because I don't have control. Okay. So what happens on the Higgs side? How do you compute what's the Wilson loop? The way to do it is to first write down what the energy density of the superfluid is. And so how do you write down what the energy density of superfluid? So the superfluid is a macroscopic quantum wave function. And so having spatial undulations causes it to have extra energy.
I'm sorry to interrupt, but so that I understand this vortex, is it the same thing as turning on a gauge field, a background gauge field that couples to the U1 and turning on a magnetic flux for that?
No.
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 I'm sorry, I said it wrong. Then what I don't understand what vortex means.
This is the ansatz. Okay.
Ansatz
So you
for-
remember, you take a bucket of a superfluid and let it rotate the bucket.
This is the superfluid's vortex.
It's exactly
Yes.
that. Yes.
So what it is for the gauge field is something. But
It's
superfluid
the
vortex because this is coupled to your phi naught.
yes, that's right.
So
Yep.
phi naught has the opposite winding.
Yes, exactly. So this carries non-zero angular momentum. Okay.
But this happens or doesn't happen dynamically. I mean, aren't you going to try to put an operator that forces this to happen?
Yes.
What is the operator?
To create this kind
You create this kind of a
it's a particle-like acceleration.
right. It's a particle like
In your
this.
path integral, you just demand that there's a winding of this object.
Yes.
That's
Yep.
what you're doing.
Yep.
I see.
Yes. Or you could also put in an external rotation in your
But are you
case.
sure this is not the same as what I said? That you take your global U1
You-
and put a magnetic field?
You could, yeah, it's the same thing. In some sense, it is because it's a background. You talked about background gauge
Yes.
field, right?
Yes.
So yes, it
Yeah,
is
so
the
then
same.
it will always be log interactive.
Yes, it is. It is log
Background,
interactive.
Not fluctuating.
Yeah.
Just reading that, okay. But
Okay.
then there's some more subtle distinctions. that
Right.
you-
Yes. So
You have so far only one vertex, no anti-vertex, just this,
just
only one vertex.
yes.
So there is a vertex. I don't know which one you are looking at, only one vertex.
I am looking at one vortex right now. Yes. So you can write down the energy density of the superfluid vortex, and all you have to do is to minimize this energy density for the ansatz that I showed you. Okay, and that will tell you what the gauge field is doing far away from the core of the vortex. That's where I care. Okay, so
You're thinking of R3 is what? R2 cross time?
no, this is in 3 space dimensions. Okay, so that's what this R3 is. Just this is a static configuration in our ordinary space. Okay, so
Are you going to have log divergence in this energy?
yes.
On cell? On
Of
cell
course.
means the solutions. The solution that
Yeah,
you will have,
yeah,
you
yeah,
put
yeah.
it back.
Of
If
Yep,
you
yep,
have
yep,
log-
yep, yep,
That's
yep.
the log
So
interaction.
these are not gauge limiting vertices. Okay, if you have vertex and anti-vertex, then you will have something finite probably.
Right. Yes.
Okay.
Yeah, that's where the log interaction will be.
Right.
That's right.
Yeah.
So, so P is the path along which the vortex core is. The Wilson loop you want to compute around the core of the vortex, very far away from the core of the vortex. Okay. And so there is a superfluid flow going around the vortex, and u theta is the superfluid velocity. So you want determinant of phi to wind around this axis. As a result, I'm just going to tell you what the phi field is going to do. It's going to have the following form. Okay, so it's going to be diagonal matrix with only one of the entries going to carry all the winding. Okay, the reason for that is that the wave function, you want it to be single valued in space. Okay, so that's why these entries cannot carry fractional windings. Okay, so it's only one of the entries of this matrix has to carry the winding. Okay, and this f of r, g of r, these are radial functions. I'm not going to solve for them. You can solve for them if you want. But what I really care about is what they are far away from the core of the vortex, and they are just 1, okay, very far away. And they go to 0 in the core of the vortex. And I'm also going to tell you what the gauge field ansatz should be so that you minimize the energy density corresponding to this superfluid vortex ansatz. And it's basically the third generator of the gauge field, of the gauge group. In this particular gauge fixed language, that's what minimizes the energy density. So I am going to parameterize it with this little a field, little a parameter. And so now I plug this ansatz in the energy density. So this is coming from the fact that the derivative here in the cylindrical coordinates is hitting this ansatz that produces this matrix, and the next matrix is just the gauge field. And so now you write down what the energy density is in terms of this little a and minimize, and you find that little a has to be 1/3 to minimize this energy density. Now, when you plug this back in here, little a in this form of the energy density, you see that this doesn't go to 0. Okay, the energy density doesn't go to 0, it goes to some number over r square. So if you computed the energy per unit length for these vortices, you would see that there's a logarithmic divergence, as you expect, because these are superfluid vortices. Okay, so you can contrast this with ordinary superfluidity and ordinary superconductivity. These are superfluid vortices because there are logarithmic energy per particle. But these are also superconducting because some of the winding, part of the winding of your order parameter is getting absorbed by the gauge field. Okay, so it's both superfluid and superconductor. It's superfluid with respect to the U1 global symmetry, superconductor with respect to the gauge symmetry. So this is what you have to do. Now you go back and compute the Wilson loop. Okay, now that you have what you know what the gauge field is doing far away from the core of the vortex, you compute the Wilson loops. And you get this, the Wilson loops are e to the 2 pi I over 3, depending on whether you're computing the Wilson loop along the direction of the flow or not. If you're computing it opposite to the direction of the flow, you would get e to the minus 2 pi I over 3. And then if you're computing the Wilson loop not around a superfluid vortex, you'll get 1. Okay? You have to now contrast this with the nuclear matter side or the non-confining side. And here, because I am doing SU3 gauge theory, in 4 dimensions, I have no control. So I'm going to just tell you, wave my hands and tell you what should happen. And this is what I expect. I expect the Wilson loop to be strictly 1 on the confining side due to confinement and string breaking. It's also a result of the fact that you expect strong fluctuations in the Wilson loop on the confining side. So if so, we have identified a non-local probe that can sharply distinguish Higgs from confinement. Sadly, we can't do calculation on the confining side for this theory. So we are going to play a different game tomorrow, which is that we're going to write a different theory where we're going to have control in both Higgs and the confining side. It's going to be a U1 gauge theory, the 2+1D model that I talked about earlier. And so it's going to let us have control on both sides, will allow us to compute the Wilson loops around vortex-like excitations on both Higgs and the confining side, and I will show that there is a sharp distinction. There's a sharp distinction between the Wilson loops on the 2 sides. So I think I should end now.